Happy to have Fermi who will tell us how to construct random unitaries.
Thanks for the introduction. Is mic working okay? Yeah. All good? Okay. Great. So thanks so much for having me. This talk is titled How to Construct Random Unitaries. This is a joint work with Robert Huang, who isn't here right now, but will be here later today. All right, so the main question of this talk is, are there efficient quantum circuits that look truly random to any efficient observer? So this refers to a pseudorandom unitary. So formally, a pseudorandom unitary is an efficient class of circuits, or an efficient set of circuits, U sub k, so the circuits are indexed by some key k, with the following guarantee, that for any quantum polynomial time algorithm A that has oracle access to U, it cannot distinguish whether this unitary U is sampled from this pseudorandom unitary family U sub k, or it's sampled as a Haar random unitary. And so when I say that this circuit, this algorithm has oracle access, what I mean is you should think of this polynomial size quantum circuit, A to the U. And so it has these sort of fixed non-oracle gates, A1, A2, up to some polynomial number. And it also gets to make these oracle queries to a black box that's implementing this unitary U. Right? And the goal of this algorithm is to decide whether or not it was given a unitary from this pseudo-random family or from a truly random a truly random unitary. Okay, and at the end, it's going to do some measurement and output its guess for which setting it's in. And a pseudo-random unitary guarantees that for any quantum polynomial time algorithm, the probability it guesses 1 in the two different worlds, in the pseudo-random world versus the Haar world, are going to be negligibly close. Okay. Let me pause here to make sure this definition makes sense. The whole rest of the talk is going to be contingent on this definition making sense. So if you have any questions, now would be a good time. Yeah. What's the definition of U? Oh, there exists some fixed polynomial that's such that these circuits can be implemented by such that these UKs can be implemented by a circuit of that size. Yeah, the efficient is coming up in two places here, right? We want that the circuits themselves are efficient, and then we want them to be secure against any efficient adversary, any efficient algorithm. Yeah. Oh, that's a really good question. I will eventually, and let me come back to that. Yeah.
Are you allowed to measure the middle of the circuit, or can they always be delayed?
They can always be delayed. Yeah, great question. Other than concerns about allowing U dagger, does the definition make sense? Okay, great. So it's been an open question since this notion was first proposed in 2018, whether these objects exist or whether we can give evidence that they exist under widely accepted cryptographic assumptions. And that's what this work is about. We give the first proof that pseudorandom unitaries exist, assuming that a cryptographic object known as a one-way function exists. So before I dive into what this work is about, let me just say a little bit more about random unitaries themselves. So today, when I talk about random unitaries, I'm going to be referring to unitaries drawn according to the Haar measure, which just intuitively think of this as the uniform distribution over n-qubit unitaries. And this is the unique measure, unique distribution with the property that for any fixed unitary W, if you sample a unitary U from the Haar measure, then U times W is also going to be distributed as a Haar random unitary. So Haar random unitaries have a bunch of wonderful and interesting properties. They produce highly entangled outputs, like this output state U applied to some fixed psi. It's going to be highly entangled really in any way you look at it across any cut. In physics, this is often the behavior of Haar random unitaries makes them incredibly useful. They exhibit these sort of things called typical behavior. Basically, it gives you a way to kind of prove statements or understand sort of properties of generic unitaries. And another thing that makes them quite useful and also potentially annoying in some cases is that they have exponential complexity. So that means that if you take a Hall-random unitary and you want to find a circuit that actually implements it, like almost certainty, it's going to require exponential depth. So Hall-random unitaries show up all throughout quantum information science. They're used to, they underlie the design of modern quantum supremacy experiments. They're used in quantum cryptography. They're used to design quantum learning algorithms. They're also used as an idealized model of physical systems. So let me say a little bit more about that. So I'm not a physicist, and this is basically just like my my impression of what's going on in this area from a very distant vantage point. But it does seem to be a common practice in physics to, at least as a toy model, pretend that real physical processes, like real like dynamics of some physical system, can be modeled as a Hall-random unitary. And this is frequently done when people study black hole dynamics. So one like serious problem with this is that we don't actually expect that any physical process corresponds to an exponential time computation. And so this is really just like a mathematical convenience. And ever since the notion of pseudorandom unitaries was first proposed, it's really caught on in some areas of physics, where a lot of papers are starting to appear proposing that pseudorandom unitaries are at least a more realistic toy model for these highly scrambling physical processes like the dynamics of a black hole. So in particular, it's sort of the existence of a PRU allows you to, in some sense, pretend that you have a polynomial size, like an efficient circuit that for all practical purposes is acting like a truly random unitary. Okay, so there's been quite a lot of prior work on building pseudorandom unitaries. This is a non-exhaustive list. And what these works achieved was that they constructed various like weakenings of a pseudorandom unitary. So in particular, they would construct these objects and prove that they're sort of like pseudorandom unitaries and that they are secure against some class of attacks, but not all efficient algorithms. And I think the state of the art of this prior work, these works of MPSY and I'm not going to actually get all these names, but where they construct pseudorandom unitaries secure against non-adaptive queries. So in particular, they construct it. They have security against algorithms that look like this, where the algorithm makes all of the queries to the unitary in parallel. Okay. So this is an interesting but not like a very expressive but not like complete class of all efficient algorithms that query random unitaries, or that query a unitary. Okay. Like in full generality, an algorithm can query the unitary adaptively and make its queries to like future calls to the unitary based on the outcomes of previous calls. But if you only cared about security against algorithms that make these parallel queries, and there are cases in which you do care about just this, we did have pseudorandom unitaries secure against this class of attacks. However, the existence, like the main question of whether PRUs exist remained open. So before I talk about what we do, I want to say a little bit, sort of my opinion, my take on why it's been so hard to construct pseudorandom unitaries. And I think like one explanation for this is that we lack these like so-called user-friendly techniques for analyzing Hall-random unitaries. So when you want to construct a pseudorandom unitary, what you're trying to do is prove a statement that looks roughly like this. You've proposed, maybe you have some ensemble of unitaries in mind, some like proposed construction of pseudorandom unitaries. But like whatever that ensemble of unitaries is, at the end of the day, you have to prove some sort of closeness between these two mixed states. One being the state of an algorithm after it queries a random unitary drawn from your pseudorandom ensemble, and the other being the mixed state you get when you query when the algorithm queries a truly random unitary. And the second mixed state, well, even that gets pretty hard to think about in full generality when you have an arbitrary quantum algorithm. And there is sort of like one common approach, like one like unifying like general approach to tackling problems like this. And it's by relating it to something called the Weingarten calculus. So the kind of recipe here is you look at an expression like the expectation over a Hall-random unitary of maybe the algorithm state after it queries this unitary some number of times. And you try to relate this density matrix to expressions that involve these things called Weingarten coefficients. And then once you do that, you reduce your problem to bounding some some expressions that involve these coefficients. And you can do this with various techniques from representation theory and combinatorics. But step 2 is where things often go wrong. And it can be like, I think it's like notoriously difficult to get step 2 to work. It requires either like looking up previously proven like asymptotic bounds on these Weingarten coefficients, or like sort of doing it in-house, like building your own bounds from scratch. And both of these things like have been done in prior works on pseudorandom unitaries. All right, so in this work, as I said, we give the first proof that PRUs exist, assuming one-way functions. And the way we do it is by analyzing this ensemble called the permutation function Clifford ensemble. Let me not say too much more about this at the moment. I'm going to come back to it later. It's going to feature pretty heavily later in this talk. But I just want to say that this is an ensemble of unitaries proposed in a prior work of MPSY. And the way we do this, though, is with a whole new technique that avoids this Weingarten calculus, avoids representation theory entirely. And it's through this new technique that we call the path recording oracle. And this path recording oracle, we see it as a new way to analyze random unitaries via entirely elementary arguments. Like you only need like basic quantum information statements, bounds, and like distances between quantum states, and that's it. And along the way, like by developing this path recording oracle framework, we also show the following fact that on the surface of it has nothing to do with pseudorandom unitaries. It says that if you have any algorithm that queries a random unitary, you can efficiently implement this algorithm, or efficiently implement or simulate this algorithm to inverse exponential trace distance, so totally efficiently. Like you do not need to sample a random unitary, which takes exponential time. You can just sort of run this algorithm, and as long as it only makes a polynomial number of queries, you get like a statistical simulation of the algorithm. Any questions here? If it's not clear what I mean by simulation, don't worry. I'm going to spend quite a bit of time like clarifying what exactly that means. All right. So we actually go one step further, and this is to respond to Jeff's question from earlier. In the original definition of a pseudorandom unitary in the work proposing the notion, they only consider security against distinguishers that query the unitary in the forward direction. But what if you want security against an algorithm that queries both U and U inverse? So what I mean is like this is the standard notion of a pseudorandom unitary distinguisher. And you could also have a notion where the algorithm has like access to both unitaries, both U and U inverse. And we would call such an object a pseudorandom unitary secure against this like larger, more expressive class of distinguishers, a strong pseudorandom unitary. And that's our second result. We show that strong pseudorandom unitaries exist, also assuming one-way functions. And we do this with a modification of the first construction. Sort of for obvious symmetry reasons, you're going to need this Clifford on both sides of the construction. I won't talk about this really at all today. This talk is mostly going to focus on the standard PRU case. Yeah.
Any reason why you don't have to also add a P?
Oh, morally, like P and F kind of commute. Yeah. Like not literally, but sort of over the randomness of, yeah. Okay, while I'm being a little bit more precise, it turns out that the F is slightly different than in the forward case. In the forward case, you can use this F can be a random binary function. And in this case, it has to be at least ternary, like a random ternary function. And my guess is that that's actually kind of inherent, but maybe talk to me afterwards. All right. So I'll try to cover 3 things today. First, I'm going to talk about a very simple like classical setting, a simple classical task, like simulating a random classical function from the point of view of a classical algorithm. And this will hopefully clarify what I mean by simulate. And then I'm going to show how what we do is kind of the quantum analog of that, or like the unitary analog of this sort of basic classical task. And then finally, to end this talk, I'm going to show that the simulator actually works, that it actually does simulate a random unitary. And at the same time, I'm going to prove that pseudorandom unitaries exist. So it's going to be like two proofs or two claims in one proof. Okay, so I'm going to start out with talking about simulating random functions. So just for one slide, let's go to the classical world. So consider a completely classical algorithm querying a completely classical object, just a random function f. Okay. So if you have such an algorithm, there is the sort of obvious way to run the algorithm, which is you sample a random function. This takes exponential time, but you sample a random function, you fix it in advance. And then when this algorithm runs, I mean, it'll carry out its steps. And then at some point, it's going to query this function for an input. And you just respond according to the truth table of the function. Okay. So that's it's like the natural way you would run such an algorithm. There's also a way to simulate this algorithm efficiently. Right? You don't actually need to sample a whole random function to run such an algorithm. What you can do is something called on-the-fly simulation, where basically you just sample the random function as needed. So let me do this formally, but it's like totally obvious. So what you do is you prepare an empty set R, and I'm going to use this notation because this is going to make the kind of generalization to the quantum setting. It's going to make the correspondence more clear. So what happens is every time the algorithm queries an input x, if it's an input x that you haven't queried before, that it hasn't queried before, then what the simulator is going to do is sample a truly random y and output that. And it's also going to record this. It's going to have to insert this ordered pair xy into the set R, and the set R is just going to maintain like what are the points we've queried so far, and how did we answer the algorithm on these previous points. And this just makes sure that if the algorithm queries an x that was seen before, that we respond consistently. Right? And this is exactly going to mimic what the algorithm expects to see when it queries a truly random function. Okay. So what this is a stateful procedure that efficiently simulates a truly random function. Hopefully this whole slide, yeah. Oh, stateful just means that like the way that we answer query T depends on like some partial information that I've accumulated along the way, right? I'm recording this set of indices that or inputs that you've queried so far, and I need to remember that in order to properly answer the next query. So I'm saying that like I need to maintain some sort of memory. Whereas in the first one, it's not stateful. I mean, every single query is answered exactly the same way. You answer it according to this function f. That doesn't change as you make more queries. Does that answer the question? Okay. Cool. By the way, this slide is not supposed to be interesting. This is like incredibly boring. But the goal is to kind of like give a basic framework for what we're about to do in the quantum setting. And I should note that there's a work of Mark Sandry that extends this simulation of random functions to the quantum setting, or to the setting where you have quantum algorithms that query a classical random function. And in many ways, like what we're doing in this work is sort of the unitary analog of what Mark does in this work. All right, so now onto simulating random unitaries. So now I want to consider a setting where you have a quantum algorithm A. It makes queries to a random unitary U, a Haar random n-qubit unitary U. And what we're going to do is give a stateful procedure that efficiently simulates this random unitary. And this is going to sort of address the claims that I made earlier, and also give us a way of understanding pseudorandom unitaries. And the connection to that is not clear at the moment, but I will get into it. So before I describe the procedure, let me establish a little bit of notation. So normally when we write like kets and we write, I don't know, like an n-bit string inside, what we're doing is we are labeling this n-bit string or we're labeling this vector by some n-bit string, and it's just going to, and these n-bit strings just denote like a set of orthonormal vectors. And it's going to be useful for me to do the exact same thing, but for sets. Okay. So when I have a set R, I'm going to let ket R denote a unit vector labeled by R. And these like set states are going to behave in in exactly the way that you would expect. So if you have two sets, two objects that are distinct as sets, then the corresponding set states are going to be orthogonal. And if you have two sets that are the same, then the corresponding set states are the same. Okay. And throughout today, these sets, they're going to have the form, they're going to be sets of ordered pairs of xi comma yi, where each xi and yi is an n-bit string. And just for convenience, and so I don't have to write so many 2 to the n's, I'm going to write capital N to denote the set 0, 1 to the n, the set of n-bit strings. Okay. And so to define or to state how we're going to simulate random unitaries, I just need to define this one object that we call the path recording oracle. And it's a linear map V that behaves as follows. So to define this linear map, I'm going to just tell you what the linear map does on a set of orthogonal basis states. So the basis states I'll consider are states of the form ket x tensor ket r, where x is an n-bit string and r is a set. It can be a set of ordered pairs of some arbitrary size. And the way that V acts on this is the following. It's going to send ket x, ket r to a superposition over all n-bit strings y, except for the ones that have already appeared in R. And when I say already appeared in R, like I'm using notation slightly, what I really mean is that I'm summing over the y's that don't appear as like one of the y elements in one of these ordered pairs. Okay. And so I'm going to sum over all these y's, and I'm going to have the superposition over y tensor the set state that you get when you add the tuple, add the ordered pair xy to the set R. So I'm growing the size of the set by one ordered pair. And actually, I want the state on the right-hand side to be properly normalized. So I should have written a normalization term there, 1 over square root capital N minus the size of the set. I'm going to suppress this, but really you should imagine that it's there. Okay. Any questions on this definition? I'm going to be using this quite heavily. I'll try to keep it on the slide, but does it make sense? Yeah. Good question. So I claim that as defined, this is to answer your question, this operator V is actually an isometry, meaning that if you start with 2 orthogonal inputs, they're gonna, and you apply V to both of them, you're gonna get 2 orthogonal states as a result. And I'm not gonna do like a formal proof, but basically the reason that this is true is because if you have the state on the right-hand side, you can reverse it and uniquely recover XR. And the reason for that is that Y does not like appear anywhere else in the set R. In that like when you have Y and R unit XY, you can uniquely determine the corresponding X that it came from, because that was the only Y, like that Y was kind of like, it's unique, right? So that restriction is what guarantees that this is actually an isometry. Does that make sense?
You have to do something if R contains every Y, you're exhausted all the.
Yeah, we're actually never going to get there, and yeah, but yeah, I guess at that point it just it's actually a partial isometry, so it just won't do anything on those states, or zero them out. Any other questions? Okay. So now, as promised, here is how we simulate a quantum algorithm that queries an n-qubit Haar random unitary. So this is the standard way of implementing the algorithm. You literally just sample the unitary and then you run the algorithm. You have some final state at the end. And now here is the simulated way to get almost exactly the same state. You start with an external register, external state, and that state is going to start out as the empty set. So this phi corresponds to the empty set, and this is the R register. And you simply replace all of the queries to the Haar random unitary with a query to this V isometry. Okay, so every time I write this V, you are applying this linear map here. And then at the end, all you do is you trace out this register. You discard it. And the central claim, like the main theorem of this work, is that these two produce nearly the same state. In particular, if you look at the state of the algorithm here, and you take the expectation over a Haar random unitary U, the mixed state you get is going to be extremely close to the mixed state you get here, where this mixed state it's a mixed state because you're tracing out the R part. Okay? And we show that these two have really, really close trace distance, a really close in-trace distance. In particular, their trace distance is t² over 2 to the n. where T is the number of queries. Union? Oh, R is a set. And so are you okay with me writing a set inside of a state? So this is just the set that corresponds to the union of R and the singleton set containing the pair XY. So R is a set of ordered pairs, and I'm just taking the set of ordered pairs and adding one more ordered pair to it. Yeah. So the number of ancillas is like variable. It's starting from like basically like empty size ancilla, and every time I'm making a query, it's storing the set state, and the set state is growing by one ordered pair. Intuitively, like these ordered pairs, it's an ordered pair of like 2 different bit strings, each of like n bits. And so the ancilla is growing by 2n bits at every query. So if you have T queries, you need 2nt like ancilla qubits. Whereas if you compare this to how many ancillas you would need to sample a Haar random unitary, that's going to be exponential in n. So this is saying that this is a way to like run a Haar random unitary, but only sample as much randomness as the algorithm can actually observe. It really is like the analog of sampling a random function on the fly. Yeah. I mean, so you have a pure state over here. Like this is the whole thing. The global state of the system is a pure state, and I'm just saying like you take that pure state, you cover up some part of the pure state, and the rest is some mixed state. Yeah, I don't know. I guess it just isn't, I guess. Yeah, sorry. I could try to clarify offline. But
that's what we want. Compared to the average.
Yeah, I want to compare it to this mixed state here. I mean, I don't want it to like totally decohere. Like this shouldn't be, I don't know, like maximally mixed state or anything. It should be some kind of mixed state. And I want it to be like, I want it to correspond to the mixed state you would get in this world here. Any other questions? Yeah. No, V is literally this deterministic object. Yeah. No. Yeah, I mean this is the definition of V.
Why is it classically random function? I mean, you need some. What determines Y from X?
What determines Y? Sorry, this is like I'm doing a superposition over all Y's.
This is sort of
Yeah. The state here is pure, but what I care about here is the mixture over the choice of like Haar random U. So I'm comparing 2 mixed states here, and they're 2 mixed states for like 2 ostensibly different reasons. The mixed state on the left is mixed because U is drawn from the Haar measure, so this mixed state here. And the state on the right is mixed because I started with a pure state and then I traced out the environment. Yeah. Oh, it's on the next slide. Actually, I'm not going to show how to do it. It's efficient though. There's an efficient procedure to do it. Yeah, I'm not going to give it in the talk, but it's in the paper.
the first call to be, it seems that you sum over returning all Y.
Yes, yes, yes.
What well there? Do the following calls to be anything?
Yes, like you have a superposition over all the Y's, but it's not like at every branch of the superposition, all but one Y is there, right? Yeah.
X is like use the same sort of code. If the X in the figure of Y2 is already in R, you still act as usual? Or?
Yeah, it does. It only cares about whether the Y. Yeah, so you can have these collisions in X. And actually, like if you want to kind of do a few like toy examples to like convince yourself that this is plausible, Like a good toy example is to just consider what happens when you take two like independent copies of 0 and apply a random u to both of them. Right? You're gonna get, in that case, like a random state side of the tensor 2, and that's like the maximally mixed state of the symmetric subspace. And so you would want this V to kind of simulate the same thing. And it turns out like the ability to have like colliding x's is precisely what's going to give you that. Yeah.
This is maybe a silly question, but why is the quantity we care about the trace distance between rho and this average versus the average of the trace distance between rho and your state A2?
Oh, good. In a lot of settings, you may want to like care about the other thing. It's just that in this application, or at least in many applications, but particularly for pseudorandom unitaries, what you care about is the actual trace distance. Like you care about what is the algorithm's view in an experiment where it's given a random unitary versus the algorithm's view in an experiment where it's given a pseudorandom unitary. I haven't connected this to pseudorandom unitaries yet, but at least it's plausible. Like that's why you'd care about trace distance. If you want to argue the algorithm can't distinguish these two worlds, and trace distance gives you a bound on your distinguishing like probability in two different mixed states. But I agree. There's many settings in which you might want to look at a different expectation, like you said, and I don't think this technique applies there. Yeah. This is the main theorem. So, yeah. Like this is the main theorem of the paper. Any other questions? Yeah. No, I can give you like an efficient like quantum circuit, or at least one that only grows with the number of queries you've made, like Pauli in n and the max number of queries t, or at least, like the number of queries made so far. Yeah, actually. Or it's sufficiently simulatable, like, sorry, V. Yeah, I guess the settings are slightly different though. Like when you're doing cryptography, you want like a family of like unitaries. And here I'm like cheating slightly by V is not actually a unitary on the original n-qubit space. And that's what makes it possible, I guess. I'm not sure if that like directly answers the question, but if this weren't true, then it wouldn't be possible to do this. Okay. Yeah. Sorry. So one difference with the T design, by the way, T designs are actually pretty closely related to pseudorandom unitaries. The like difference between T designs and pseudorandom unitaries is that in a T design, you have to fix T in advance, and that determines your construction. Like there is a max number of queries you can handle. And a pseudorandom unitary is an object where you can fix it in advance and then later be secure against any polynomial T. You'll be indistinguishable to algorithms that make any polynomial T. But also you have to relax the indistinguishability to be like indistinguishability to efficient algorithms. So there's a few differences there. And then between pseudorandom unitaries and T designs and this like weird object, the former is like a class of actual unitaries, like n-qubit unitaries. This is not an n-qubit unitary. This is like something that's acting on the n-qubit space and some outside environment. Yeah. No, it starts as the empty set here, but then after the first query, it becomes a set of size 1. Right? Because the definition of V is it grows R. And so after T queries, you would expect R to have, it's going to be a superposition over sets of size T. Yeah. Yeah. Yeah, it's saying that you can spoof the randomness of Har with this object, this like deterministic object. Yeah. Yeah. If you send in the classical, good. So the question was, if you send in classical x's many times, you'll get the same y every time, and you can like verify this. In the quantum setting, if I send in like the same, like let's say like 0 every time, I shouldn't get like the same y every time, but I should get the same like har random state every time, right? Like I'll get copies of u applied to 0, right? Yeah, let's say my input is like x being the all 0 string. And if I query like, you know, the unitary on 0 10 times, I should have in my space like 10 independent copies of like the same har random state, right? It should be u applied to 0 to the tensor 10. And so what is that mixed state? That mixed state is actually the maximally mixed state over the symmetric subspace. Like if you have a har random state, you get multiple copies that corresponds to the maximally mixed state over the symmetric subspace. And you can show that that's actually what you're going to get here too, or really, really close to that. You're going to get this like superposition over like all these different y's where the x coordinate is always 0. And I think I'm doing a bad job explaining this, but if you write it out, you'll see that like the definition of this is going to give you something that looks sort of like a purification of the maximally mixed state in the symmetric subspace. Okay, so maybe I'll go a little bit low on time. So I'll go quickly. Just to give a simple example of this, just imagine you do one query on the all 0 state. In the standard case, you're going to get a har random state, just one copy of it. In the simulated case, you're going to get this this state here, the superposition over all y's of y tensor a set containing the ordered pair 0y. If you think about it, like the 0 isn't really doing anything. This is really just the maximally entangled state. And so both of these correspond to the maximally mixed state. In the first case, like just a har random state over the randomness of u is maximally mixed. In the second case, you have a maximally entangled state, you're tracing out half of it. I originally was going to do more examples, and then making the slides, I realized it's really hard to do them on the slides, but just trust me or maybe try it yourself. You can do this with like 2 copies or 2 queries in a row, whatever you want. And the theorem's true. I want to say a few more things about simulating functions versus simulating unitaries. And really, like the resemblance between the two is quite striking, I think. In both cases, you get this efficient and stateful simulation of this exponentially complex random object. Both cases, you start with this initial state R, that's like the empty set. And at each query, well, I'm lying a little bit on the left-hand side. I'm assuming you're querying on a new X. But each query, like they look remarkably similar, right? The way that you simulate a query to a random function is you take your X and you map it to a random Y, and then you update your set R by adding XY, the XY ordered pair to the set. And in the random unitary case, you're taking this cat X, cat R, and mapping this to the superposition over Y's of cat Y tensor R union XY. And in the left-hand side, the simulation is actually perfect. On the right-hand side, we have this t squared over 2 to the n error. And actually, if you really wanted to nitpick, I think that this is like a closer classical analog of simulating a random unitary is simulating a random permutation. A permutation from 0, 1 to the n to 0, 1 to the n. Yeah.
Every time you apply a
Yeah. 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 Sure. Right. Yes.
But like these spaces are not produced by like adding in like net products, right? Like it's not like a sequence of adding in cells. It's with direct sum precision. So if I'm thinking about it, adding in a small number of cells, how many do I need?
There is a way, like when you make the teeth query, there is a way to implement this by just creating 2n additional ancilla wires, and then running an operation that's like polynomial in n and t, like a quantum circuit that's polynomial in n and t. Would this answer your question? Like if you believe this was true? Okay, cool. So yeah, maybe take me my word that that's true. It's in the paper, but I won't talk about it today. Okay. I think another benefit or side effect of this like path recording oracle, so like beyond PRUs, this just gives you a completely new way to analyze random unitaries. Pretty much anytime you have an expression, or anytime you're considering an algorithm that's querying a random unitary, it seems plausible to me that this technique might allow you to say something. So we give one example of this in our work, which is we use this technique to reprove this so-called gluing lemma, proven in a recent work of Schuster, Haferkamp, and Huang. And this lemma was used to prove a very general statement about how you can compress the depth of any pseudorandom unitary. The lemma says, though, is that if you have two independent Hall-random unitaries, like U1 and U2, and they're overlapping on a small number of qubits, just any super logarithmic number of qubits, then their composition, like if you had a button and every time you press this button, it applied U1 followed by U2, then you would not be able to tell whether you had access to that button or a button that implements a truly Hall-random unitary over the whole system. So it says two overlapping random unitaries look random. The original proof of this uses the Weingarten calculus. It's actually not too bad, but does require quite a bit of technical machinery. But using this like path recording oracle view, there's a totally elementary proof now where you take each one of these Hall-random unitaries U1, U2, U3. Because they're independent, you could replace them all with sort of like separate instantiations of this path recording oracle V. So you get a V1, V2, and V3. They all have like their own separate like purifying register. And it's just kind of like an elementary argument that shows that that like the composition of two of these oracles, V1 and V2, just implements or is very close to implementing just a single larger oracle. So this is just like bounding the distance between like some quantum states. So I think it gives just a new way to kind of think about any sort of statement about algorithms that query a random unitary. And I expect there's probably many more applications to be found. And actually, like several papers have already appeared publicly that have like directly used this technique to prove new statements about random unitaries. Yeah. 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 V1, V2, V3 all have the same definition. I'm just applying them to like different size spaces. Yeah. No. No, there would almost certainly be a different V that corresponds to like Hall-random orthogonal, but this one definitely doesn't. Like you can test it. If you do, I think like U and like U dagger or something to like an EPR state, you can test that what like U is like Hall-random orthogonal versus Hall-random unitary. And this thing will behave according, like if you do the corresponding thing with a V, it's gonna correspond to Hall-random unitaries and not orthogonal. What? What supplies you with an imaginary unitary? What does that mean? Yeah, but I'm working with a larger space, and that's kind of how I'm allowed to get away with not having any imaginarity. Like I have this purifying environment, and I guess it just turned out to be true that when you're looking at this larger space, you don't need imaginarity to simulate something that has imaginarity on a smaller space. But if we take it offline, I think I have about 15 minutes, and I want to say a little bit about how this is actually proved. Okay, so I've said a lot about what you can do with the simulator. So now it's time to actually prove that this works. That it actually simulates a Hall-random unitary, and at the same time that pseudorandom unitaries exist. So to say what I want to do, let me define this PFC ensemble from MPSY a little more carefully. So this is going to be an ensemble of random unitaries U of the form P times F times C, where the other way, C is sampled from any n-qubit unitary true design. So this is just a distribution on unitaries with the property that the second moments exactly match the second moments of Hall-random unitaries. F here is going to be a random function, a random binary function applied in the phase. Okay, so it maps ket x to -1 to the f of x times ket x. And I'm going to sample a truly random binary function f, or Boolean function f. Finally, P is going to be a random permutation applied in place. So it maps ket x to ket pi of x, where pi is some random permutation on n-bit strings, or random permutation on capital N. Okay. So what I'm going to prove, the main lemma, is that queries to this a truly random PFC is indistinguishable from queries to this path recording oracle V, this isometry V. This is the main lemma. And this lemma gives you both things we wanted to prove at once. So first, this tells you that V is indistinguishable from a Haar random unitary. And the reason for that is that this lemma is true for any n-qubit 2 design. In particular, like the Haar measure, like a Haar random unitary itself is a 2 design, trivially. And I can plug in C being a Haar random unitary. And when C is Haar random, then PF times C is also Haar random. This is like the invariance property of the Haar measure. And so it says that a Haar random unitary here is indistinguishable from V. The second result, that pseudorandom unitaries exist, we're going to plug in C sampled from an efficient 2 design, in particular, like you can pick the Clifford group. And also to make the whole thing efficient, to make the P and F efficient, we're going to have to use prior results from cryptography that say that you can construct pseudo-random versions of these objects, objects that are just as good as random from the point of view of any efficient quantum algorithm. And this is where the one-way functions come in. So to recap, like plugging in C being Clifford and making PF pseudo-random is how you get the pseudo-random unitary construction. Yeah. This is a function applied in the phase. Yeah, like if I input, yeah. So we originally planned to kind of like take questions in the last 10 minutes, but should I just kind of show the, okay. So let me kind of give the sketch of how we prove this main lemma. And a big part of it comes from actually just looking at queries to a random PF. Like we're going to put aside the 2 design. It's going to come back in for the very end. And just think about what happens when you query a truly random PF. And what operation does that correspond to? When I apply the F, it's going to take ket x to -1 to the f of x. It's going to put that in front. And then applying the P is going to relabel this ket as pi of x. So PF maps ket x to this guy over here. And the idea for how we're going to analyze this is using purification. So instead of querying a truly random permutation pi and a truly random function f, I'm going to imagine a superposition over all choices of permutation pi and over all choices of function f. And I'm going to have the superposition, this exponentially large number of qubits sitting on some external register. And the idea is that instead of looking at this setup where I have PF being random, I'm going to look at this setup where I have this superposition, and I've replaced the queries to this random PF with this controlled PF query. So this is a, yeah. Go ahead.
I thought I understood your previous, my question was scenario that here can't I take f to be like f pi inverse? This is another random function.
The reason, like one way to see that this is not the same as just a query to f is if I query f on 0 and then I measure it, I will always get 0 because the result is just to change the phase. But if I do it with PF, I will not get 0. So here I'm going to have this controlled version of PF where I'm going to read the pi and f that's stored on these registers and apply the corresponding like map to these registers here. And I claim that these two are going to produce exactly the same, like these are exactly the same from the point of view of the algorithm who can't see these purifying registers over here. And the reason for that is you could imagine just measuring pi and f over here. And this measurement commutes with all of these controlled operations. And so it would be the same as like measuring pi and f over here, which is the same as sampling a random pi and f. Okay. So this is like the first step is sort of totally elementary. I'm just replacing the randomness with a purification. Good. Okay. And now what I'm going to do is I'm going to relate these queries to this controlled PF oracle. to the path recording oracle V. Okay, remember it looks like this. And I'm not going to show they're exactly the same because remember I still need to put the Clifford in somewhere. But I'm going to show that they are like spiritually like quite similar. And before I show you how that works, let me just remind you, or let me just give you this intuition for how I'm going to think about what V is doing. When you make a query to V, what you're doing is you're taking this ket x and you're mapping it to a superposition over all the y's, except for a few outliers. So you map this to a superposition over all the y's. And at the same time, like in the branch where you map it to y, you're going to record in the purification this ordered pair xy. Right? And we're going to show that this controlled PF operation does something quite similar to this. So what is a controlled PF query? I'm just writing down the definition again. It's taking x and mapping it to pi of x. And it's doing it based on this pi and f over here. Oh, and also putting this phase out in front. And I want to make one like totally superficial change to this. It's going to be helpful to rewrite ket pi of x as a superposition over all y's of ket y times this delta function, where this delta selects out y being equal to pi of x. They're literally the same thing. But it's going to be helpful to write it that way. And so I can think of my controlled PF as the exact same thing as above, but plugging this in. Like, can people see the pink? Is that a little? Okay. So now on the first query to controlled PF, what do I have? Remember, let's say I have a ket x on my query register. On the pi and f register, I have this uniform superposition over all pi and f. And all that happens when I query this oracle is I'm just going to pick up these coefficients, right? I'm mapping this x to a superposition over all y's, and then I pick up these pink coefficients. And this is just going to happen to every query. Like every time you query, you're going to map any x to a superposition over all the y's. And at the same time, you're going to pick up this delta coefficient and this -1 to the f of x coefficient. And after t queries, your purifying register is going to be a superposition over different x's and different y's of just a uniform superposition, but where you've picked up all these coefficients sort of along the way. And this gives you sort of a different way to think about what this controlled PF operation is doing. Particular, if you define these states PF sub R, where R is any set of tuples, set of ordered pairs xi, yi. If I define this to be the uniform superposition over pi and f, where I've picked up the corresponding coefficients that correspond to the set of ordered pairs, then when I write the controlled PF operation in terms of these PFR states, the controlled PF operation is performing this map. This is just kind of like an elementary way of like rewriting what controlled PF is doing in this very special basis that kind of, I think, illuminates the action of this map a little better. It's doing this operation. X gets mapped to the superposition over y's, and at the same time, you introduce xy into this set, which correspond to like throwing on like one more delta and one more -1 term over here. And just sort of compare this to what the map that V does, like nearly identical. Which ones? The PFR states? Good question. Sort of. You can show that these PFR states are truly orthogonal when the xi's are all distinct from each other. So sort of on most of the inputs, these two maps are doing exactly the same thing. And then on these bad inputs where the xi, sorry. On these bad inputs where the xi's are, sorry, is there a question? Okay. On these bad inputs where the xi's are distinct, like that's where the algorithm can actually distinguish that it's interacting with this guy and not B. Okay. So actually CPF is easily distinguishable from B. Like this tells you kind of how you would distinguish. There are ways to distinguish by querying on xi's being distinct or not distinct. And intuitively, like when the xi's collide, they kind of get erased from here because the -1s will cancel out. Yeah, about done. So what I'm saying is like if you relabel these PFR states as ket R, and remember like this is like on the purifying register and you don't get to see this. So you can kind of relabel that register however you'd like. Then these oracles behave identically except on these bad R states, right? Where you have collisions in the xi's. And this is where the two design that I put aside comes back in. What we show is that inserting C sample from a two design before each query forces the algorithm or ensures the algorithm can only place a negligible amount of weight on these bad input queries that allow you to distinguish these two oracles. And that's basically the whole proof. So the recap is we define this path recording oracle object, and using this purification argument, we showed that you can't distinguish between queries to random PFC and queries to this recording oracle V for any two design C. And as a consequence, you get PRUs and that V simulates hard random unitaries. One slide really quick on inverse queries. I only talked about queries to U, but not U dagger. In the paper, we show that there is this sort of symmetric version of this oracle that allows you to simulate queries to forward and inverse access to a hard random unitary. And as a result, we get pseudorandom unitaries secure against forward and inverse queries. We call these strong PRUs. And so it kind of has like the analogous guarantee, the guarantee you would expect. And this turns out to be like an order of magnitude harder than the forward case. And kind of conceptually, the challenge arises from the fact that it's not sufficient anymore to just record the path. Like you're not always just going to add an ordered pair to the set. You also have to have some mechanism to erase elements from the set when you have inverses, because you want things to be able to cancel out. So let's see the paper for how that works. And let me just put the future directions up on the slide and here. All right, thanks so much.
We maybe have time for one quick burning question. There.
So I guess in these recent related papers, I think they somehow also discuss of this collision-free as like a one key conceptual simplification of this algorithm. Could you compare this, the way that different papers use it, and how it compare with how you like, you know?
Oh, are you asking about like the other like MPSY and like other things like?
I think in all these recent paper in getting T designs and PR, like it's both non-adaptive one, and it seems that in your paper as well.
Yeah.
So
Yeah.
this is one key feature, and how would you compare these?
Yeah. So like we're certainly not the first to notice that like this PF construction has nice properties when you don't have collisions. Turns out that like kind of getting the right argument to go through though when you have adaptive queries, it's much easier to make it work when you have this purification. And intuitively, it's because the purification kind of lets you do an argument about kind of what happens on the purifying register, and this helps you capture the distinctness somehow. But I can talk to you about it offline. Okay, thanks.
Let's thank Fermi again.